Have you ever needed to shovel snow from your driveway? Not as SoCal residents. In a funny twist of fate, we got the opportunity to investigate how a snowblower works for our FMD project. Our snowblower makes y'all's life easier by using a two-stroke engine to drive a belt that then rotates a set of rubber blades located on the bottom of the snowblower. Those rubber blades then redirect the snow upwards and ultimately to the side. After disassembling the snowblower, the main fluidic device we decided to focus on was the carburetor for the two-stroke engine, which is what creates and controls the air-fuel mixture going to the engine for combustion. The carburetor system consists of a venturi, two butterfly valves, a fuel reservoir, and a float valve within the fuel reservoir. The air-fuel mixture is most directly controlled using the choke valve, and the volumetric flow rate of the mixture through the engine is controlled using the throttle valve.
Using our knowledge gained through this class, we decided to first do a lossy analysis of the full carburetor system. The purpose of this analysis was to determine an approximation of the manifold pressure with a throttle and choke wide open, so we could then compare it to the PATM/3 estimate given in the textbook. We started off using the estimated max RPM for the snowblower found online, which is 4,000 RPM, to calculate the volumetric flow rate Q through the system at max throttle using the relation Q is equal to the volume displaced per revolution times the revolutions per second. From there, we then use the relation Q is equal to UA and Bernoulli's to define the velocity and then the pressure at the throat of the venturi within the carburetor, using a streamline connecting the throat to atmospheric pressure far away from the carburetor. With the pressure at the throat then determined, we did two lossy Bernoulli analyses to find the pressure at the manifold. The first lossy analysis we did was for the rapid expansion following the venturi throat, for which we used the following Moody chart to find the viscous dissipation factor needed for the calculation. From there, the second lossy analysis we did was for the region approximated as a straight pipe that connects the location post-throat expansion to the throttle and the manifold. After completing that series of calculations, we found a manifold pressure of 0.45 times PATM, which is on the same order as the PATM/3 that the textbook estimates as the manifold pressure. Comparing the solution we got to the solution you would get without doing a lossy analysis, it becomes clear why a lossy analysis is critical to properly understanding the system and how it functions. As shown in this plot, a lossless analysis concludes that the manifold pressure would approximately equal atmospheric pressure if the areas at the beginning and end of the carburetor are the same, which is incorrect.
We next calculated the approximate air-to-fuel ratio for an open choke valve, assuming that the speed of the air at the throat was 216 meters per second, as we calculated previously. The air-to-fuel ratio is equal to the mass flow rate of air over the mass flow rate of fuel, and m dot is equal to rho UA. We know the density of the air and the density of the fuel, as well as the cross-sectional areas of the fuel intake into the throat and the cross-sectional area of the throat itself. So all that's left to find is the speed of the fuel entering the throat, which can be done through a combination of a free stream analysis and a lossy tube analysis. Looking at both equations for the fuel speed for a free stream and for the Bernoulli loss through a pipe, they both reference the change in pressure and the speed of the free stream. We know that the final speed of the fluid must be a function of both equations and therefore can solve that system for U. When we plug in all of the numbers, assuming the pressure of the fuel reservoir is atmospheric, and the length of the line connecting the reservoir and the throat is 30 millimeters, we get the speed of the fuel to be 0.95 meters per second as it enters the throat. Using the cross-sectional area of the fuel line, we get that the fuel flow rate at the throat is 4.7 times 10 to the minus 6 meters per second, and the fuel pressure at the exit of the fuel line is 101,288 pascals, or 99.9% of atmospheric pressure. The air-to-fuel ratio can now be calculated using the mass flow of the air and the mass flow of the fuel at the throat. This then gives us a maximum air-to-fuel ratio of 24.6.
The last analysis we did for the carburetor was to look at how the pressure drop across the throttle changes as a function of throttle angle. As the throttle angle decreases from 100% open toward this closed position, the throttle valve itself starts to act more and more like a bluff body, which therefore increases the drop in pressure across the throttle valve. That drop in pressure, from form drag, starts to become non-negligible as the throttle valve closes, due to the separation that begins to occur on the back edge of the throttle valve, which overall causes the system to have larger losses and therefore causes the delta P across the valve to increase.